Hello everyone, welcome to the video on Variants of Gradient Descent by Society of Artificial Intelligence or SOAI. I am Ritul and these slides are created by my colleague Tushar. Let's start. A quick history of DL to set the context. The following illustration shows the progress of deep learning over the last 3 decades. A timeline of where we are. The DL story. Better learning algos, better initialization, better activations and better regulations. From 2006 to 2019, we are having more data, more computation, more democratization. When we talk about from 1989 to 1991, we are having UAT and backpropagation. From this, we can decode that from last 3 decades, we are having more democratization, which means the DL is growing and growing. Some of the salient points in the DL timeline are as follows. From 1889 to 1991, there are universal approximation theorem. We will be able to approximate any kind of function with our neural network. Backpropagation, derivative calculation happens backwards from the output layer to the input. That is, backpropagation, it is nothing but gradient descent applied with the chain rule. Next, in 1993 to 1994, a lot of work was done on recurrent neural networks. And 1998 LSTMs, long short-term memory, were proposed. Work from on convolutional neural networks. When we talk about 2006, we was having revival of DL by Hinton et al. With the proposal of unsupervised pre-training. People's interest in deep learning started increasing. In 2019, better learning algorithms, initializations, activation, and regularization, more data, compute, and democratization. Variants of gradient descent, highlighting a limitation of gradient descent. The gradient descent update rule is as follows. You can see in the second line, the questions we should be asking are how do we compute the gradients? What should data we use for computing the gradients? To follow up on those questions, how do we use the gradients? Can we come up with a better update rule? Here is the Python implementation of gradient descent similar to what we have seen earlier. Look at the following plot of W, B and error using gradient, which is on the next slide. Here it is, highlighting a limitation of gradient descent. You can see this is the coding part and the output is generated like this. Here x and y are the variables which were analyzed in first two lines. You can see in this coding part, and when we move to the function f with parameters w, b, x, here sigmoid with parameters w, b, which returns this statement you can see in the very first function here. And when we talk about the next function, which is error function with parameters w, b, here error initialized 0 for x, y in zip x, y. Here fx is equal to f function with parameters w, b and x, and error plus is equal to 0.5 into fx minus y with power 2, and this function will return error. Similarly, next function, which is grad underscore b function with parameters w, b and x and y. Here fx is the variable which stores the data returned from the function f with parameters w, b and x. This whole function return fx minus y multiplied with fx multiplied with 1 minus fx. Next function is grad underscore w function with parameters w, b, x and y. Here fx is equal to function of w, b. Fx is equal to function called f with parameters w, b and x, which return fx minus y multiplied with fx multiplied with 1 minus fx multiplied with x. You can see in this statement. Next function is do underscore gradient underscore descent function. In this you can see w, b, eta is equal to minus 2, minus 2, 1.0. Here w is equal to minus 2, b is minus 2 and eta is equal to 1.0. Max underscore epochs is equal to 1000. Here is the max underscore epochs initialization with 1000. For I in range max underscore epochs. dw, db is equal to 0, 0. for x comma y in zip greater x comma greater y, dw plus is equal to grad underscore w function with parameters w, b, x and y. And in the next statement, db plus is equal to grad underscore b function with parameters w, b, x and y. And w is equal to w minus eta multiplied with dw, and b is equal to b minus eta multiplied with db. You can see in this graph here, this represent closely spaced points indicate very smooth or gradual slope. This one. And these dots are disjoint points indicate very steep or slope. A deeper look into the limitation of gradient descent. First, let us look at function to illustrate how the slope behaves. So, if the derivative is small, the amount by which w or b will be updated by is also small, and vice versa if the derivative is large. This could become a problem as in the low scope or flatter regions the algorithm does not move fast enough. Here is an example of gradient descent running inefficiently, moving too slowly. If it is to happen that a random initialization of W and B start at a flat region, then the algorithm would need to run many epochs to get out of the plateau. We need to find a solution for dealing with low scope regions. Here, in this graph, you can see this. This is the gentle slope low derivative 1 by 1, which is equal to 1. And this one is steep slope high derivative 3 by 1, which is 3. Here, this line represents by function fx is equal to x square plus 1. Delta y1, which is slope, that is how much does y change when x changes. Slope is steep tends to derivative high, when slope is gentle derivative low. Introducing contour maps. Look at the following image to understand how contour maps help visualize 3D data into 2D. You can see this here. This is slope, and from gentle slope to steep slope, and each horizontal slice indicates a region of uniform error. And when we move to here is this, from short distance corresponds to the steep slope, and long distance corresponds to the gentle slope, and from each ring has a uniform error. This figure represents the top-down view of the sliced curve on the left. Some interesting points to note. The rings or contour in the top-down plot each indicate a uniform loss along the contour boundary. A small distance between contours indicates a steep slope. A small distance between contours indicates a steep slope along that direction. A large distance between contours indicates a gentle slope along that line. These are the main points to remember when reading contour plots. Look at the following contour plots and guess their 3D contour parts. These are contours and these are 3D plots. Correspond to the contour. You can see in this here. Henceforth, we will be showing the gradient descent movement on a 2D contour map. Visualizing gradient descent on a two-dimensional contour map. Now we will visualize gradient descent on a 3D map and then its corresponding 2D map. Here is the 3D plot that we have seen many times before. This one. And now let's look at the same gradient descent plotted in a two-dimensional contour map. This is here. In both of the plots, the GD line eventually reaches the center of the dark blue region. Intuition for momentum-based gradient descent. One of the main issues with gradient descent is that it takes a lot of time to navigate regions with gentle slopes, because the gradient is very small in these regions. An intuitive solution would be that if the algorithm is repeatedly being asked to go in the same direction, then it should probably gain some confidence and start taking bigger steps in that direction. Now, we have to convert this intuition into a set of mathematical equations. Consider the following equations. Gradient descent update rule, which is Wt plus 1 is equal to Wt plus eta delta of Wt. Momentum based gradient descent update rule. Here you can see in the A, B and C statement. The D statement is like if y multiplied with u, then it is the same as the regular descent update rule t minus 1 is equal to 0. To put it briefly, ut-1 is the history of movement in a direction and y ranges from 0 to 1. Dissecting the update rule for the momentum based gradient descent. Let us further dissect the momentum based gradient descent. Ut is equal to y multiplied with ut minus 1 plus eta of delta w. This variable is called the history. And wt plus 1 is equal to wt minus ut. This variable represents the current movement to be made. Consider every instance in time denoted by the subscript ranging from 0 to t. Here u0 is equal to 0 and u1 here is y multiplied with u0 plus my eta multiplied with delta of w1, which is again equal to eta delta w1. You can see from 5th to 10th statement. The 11th statement is what here we take an exponentially decaying weighted sum, whereby as we move further and further into the series, the weight decays more. The intuition behind this is as we progress further and further down a series or direction, we can place lesser and lesser importance to the later gradients as we move along the same direction. Running and visualizing momentum based gradient descent. Here is the Python code for momentum based gradient descent. Here is the code, which is again very similar to the previous code. Now let us compare the movement of momentum based GD and regular GD. Here gradient descent is like here and we have 40 epochs and momentum based gradient descent is this with 29 epochs. However, there are still some issues with momentum based GD that we will address in the next section. A disadvantage of momentum based gradient descent. Observations. Even in the regions having gentle slopes, momentum based gradient descent is able to take large steps because the momentum carries it along. Questions. Let us look at an implementation momentum based GD. A few points to note. Momentum based gradient descent oscillates in and out of the minima valley. U-turns. Despite these U-turns, it still converges faster than vanilla gradient descent. Now, we will look at reducing the oscillations in momentum based GD, that's gradient descent. Intuition behind Nesterov accelerated gradient descent. Let us consider the momentum based gradient descent update rule. Here, this is the update rule in A, B, C statement. When we move to the D statement, here we can see that the momentum occurs in two steps. The steps are the first is with the history terms y multiplied by ut minus 1 and the second is with the weight term. When moving both steps each time, it is possible to overshoot the minima between the two steps. And the fourth is, so we can consider first moving with the history term. Then calculate the second step from where we were located after the first step. Using the above intuition, the Nesterov accelerated gradient descent solves the problem of overshooting and multiple oscillations. W temp is equal to Wt minus y multiplied with ut minus 1. Compute based on movement with history temp. Similarly, Wt plus 1 is equal to W temp minus eta of delta W. Move further in the direction of the derivative of W temp. Update history with movement due to derivative of W temp. Running and visualizing Nesterov accelerated gradient descent. This is the Python code for NAG. It is an improvement on the MGD. First of all, I should recommend to go through the code, which is again quite similar to the previous one. And here we have a comparison between NAG and MGD. First of all, give a side to this graph. Here, looking ahead helps NAG in correcting its course quicker than momentum based gradient descent. Hence, the oscillations are similar and the chances of escaping the minima valley are also similar. Here, black is MGD and red is NAG. Summary and what next? We have seen two new update rules, namely momentum based gradient descent and Nesterov accelerated gradient descent. These each mitigate some of the shortcomings of vanilla gradient descent. MGD allows for faster movement at plateau regions, thereby saving a lot of time or epochs. However, MGD can be a bit wasteful as it approaches the minima valley and oscillates till it stops. This flaw was remedied using energy, whereby oscillations near the minima valley are drastically reduced. Energy offers a good improvement to MGD. The idea of stochastic and mini-batch gradient descent. Let us consider vanilla gradient descent. From the above image, we can see that we make one update function with w, b for one pass or epoch over the data. Here, x and y initialized, and there is the function do underscore gradient underscore descent function. In this function, we have w, b, and eta as well as variables which are initialized as -2, and 1.0. Here, max epochs is equal to 1000. For I in range of max epochs, dw and db initialize as 0 and 0. For x, y in zip greater x, greater y, dw plus is equal to grad underscore w function with parameters w, b, x and y, and db plus is equal to grad underscore b function with parameters w, b, x and y. Again, w is equal to w minus eta multiplied with dw. It is the update to w are made only after all data points are covered. Similarly, in the next statement, d is equal to b minus eta multiplied with db. It is update to be made only after all data points are covered. It can be exemplified as follows. Consider a training set with 1 million data points. With gradient descent, we calculate the derivatives for each of these points. Once we are done, we update the parameters. Thus, we pass over all 1 million points to make a single update to W and B. It can also be called batch gradient descent as the entire dataset is used as a single batch. However, we can choose to make an approximation based on looking at a smaller portion, which is batch, of the data points instead of analyzing the whole dataset each time. The idea of stochastic and mini-match gradient descent. This is called mini-match gradient descent and can be described as follows. Consider a training set of 1 million data points. Select a batch size of 100 data points. What this means is that every batch, the algorithm calculates all of the 100 derivatives and updates the parameters. Thus, passing over all 1 million data points result is 10,000 updates to W and B. Stochastic gradient descent is when the batch size is 1. That is an update to the parameters after each single data point. One key thing is to note is that both stochastic and mini-match gradient descent are approximations of the true derivative obtained by match gradient descent. However, it is advantageous as it allows us to make update faster and achieve quicker progress. Running stochastic gradient descent. Let's do a side-by-side comparison of batch GD and stochastic GD. Here batch GD is the function with 2 underscore gradient underscore descent function with parameters. In this function w, b, eta is equal to -2, -2, 1.0, and max underscore epochs is initialized with 1000. For I in range of max epochs, dw, db is equal to 0, 0 for x, y in zip greater x, greater y. dw plus is equal to grad underscore w function with parameters w, b, x and y. In the next statement, db plus is equal to grad underscore b function with parameters w, b, x and y. Here, w becomes w minus eta multiplied with dw and b becomes b is equal to b minus eta multiplied with db. And this is the batch GD graph. And when we move to the stochastic GD, the graphs look like this, and you can see this is more and more finer. Stochastic GD. In this do underscore stochastic underscore gradient underscore descent function, we initialize w, b, eta, max epoch like -2, -2, 1.0 and 1000. For I in range of max epochs, dw, db is equal to 0, and for x, y in zip x, y, dw is equal to grad underscore w function with parameters w, b, x and y. db is equal to grad underscore b functions with parameters w, b, x and y, and w is equal to w minus eta multiplied with dw. B is equal to b minus eta multiplied with db. Here is the difference between the batch GD and stochastic GD. In the batch GD, the last two statement, that is w is equal to w minus eta into dw, and statement b is equal to b minus eta multiplied with db is iterate, for I in range of max epochs. But in the stochastic GD, these two statements iterate in the for x, y in zip x, y. Some of the advantages of stochastic GD are quicker updates, many updates in one pass by the data. Some of the disadvantages of stochastic GD are approximate stochastic gradient. Almost like tossing a coin once and computing P. Almost like tossing a coin once and computing probability of heads from the gradient descent which visualization we have seen that it oscillates during movement. However, this oscillation is different from momentum GD or NAG. In stochastic GD, the oscillations are due to redirection after every point, as every point behaves as a individual greedy entity influencing W and B, thus leading to fluctuations right from the start. In MGD or NAG, the oscillations appear the value epochs the minima as a result of overshooting the intended destination. Let's look at the Python implementation of mini-batch GD. Now let us look at the two-dimensional visualization of mini-batch superimposed over stochastic GD. Here we can observe that even though the plot oscillates for mini-batch GD, it is still considerably less than with stochastic GD, evidenced by the red plot lying entirely within the blue plot. As we increase the batch size, the stability of the curve also improves, the resulting in better estimates of the gradient. Recommendation batch size is 32, 64 and 128 etc. The higher the batch size, the more accurate the estimates. In this code, with function do underscore mini underscore batch underscore gradient underscore descent function. Here we initialize W, B, eta and max impose as minus 2, 1.0 and 1000. And mini underscore match underscore size is initialized as 10 and num underscore points underscore scene is initialized as 0. For I in range of max underscore epochs, dw and db is first initialized as 0, 0. For x and y in zip with greater x, greater y, dw plus is equal to grid underscore w function with parameters wb, x and y, and db plus is equal to function with parameters wb, x and y. And here num underscore points underscore scene plus is equal to 1. After this, you can see if num underscore point scene modulo of mini underscore point underscore size is 0, then w becomes w minus eta multiplied with dw and d becomes b minus eta multiplied with db, and the output comes in like this graph. Variants of gradient descent, epochs and steps. Let us go over the definitions of an epoch and a step. One epoch is equal to one pass over the entire data. One step is one update of the parameters. N is the number of data points and B is the mini batch size. Let's analyze the algorithms using epochs and steps. Let's look at the stochastic version of NAG and momentum based GD. Since there is a history component, NAG and momentum, GD have slightly smoother oscillations. Since there is a history component, NAG and momentum GD slightly smoother oscillations. Algorithm and number of steps in one epoch. Batch gradient descent is 1 and stochastic gradient descent algorithm is n number of steps in one epoch, and mini batch size gradient descent algorithm has nb number of steps in one epoch. Stochastic momentum GD. Why do we need an adaptive learning rate? Consider input data with 4 features being processed through a sigmoid neuron. Here y is equal to function of x, which is equal to 1 divided by 1 plus e with power minus of w dot x plus b. X is equal to x1, x2. Here you can see the value of x and w. From our gradient formula, we know that the value of the input features play a role in the gradient calculation, that is here you can this represent in this here, which is function of x minus y the whole multiplied with f of x multiplied with 1 minus f of x and again multiplied with x with power n. In real world scenarios, many features in the data are sparse, that is they take on a zero value for most of the training inputs. Therefore, the derivatives corresponding to these zero valued points are also zero and the weight update is going to be zero. To aid these sparse features, a larger learning rate can be applied to the non-zero valued points, these sparse features. You can see in this image there is many inputs from B, W with power 4, W with power 1, power 2, power 3, and the output is in only Y passing through a function. Example: consider a object at college that you are taught for only 5 minutes a day. For those 5 minutes, maximizing attention span would allow for maximum knowledge retention. In this case, the 5-minute subject would be a sparse feature, that is, a feature that does not occur very often in the training data. And the attention span would be a learning rate. A high learning rate for the sparse features allow us to maximize the learning we get from it. It's also known as weight updation. Conversely, dense features are those with non-zero values for most of the data points. They must be dealt with by using a lower learning rate. Can we have a different learning rate for each parameter which takes care of the frequency, sparsity, or density of features? Variants of gradient descent introducing adagrad. In division, decay the learning rate for parameters in proportion to their update history. Fewer updates, lesser decay. The adaptive gradient is an algorithm which satisfies the above intuition. Here, adaptive gradient is also known as adagrad, which is this value increments based on the gradient of that particular iteration, that is, the value of the feature is non-zero. In the case of dense features, it increments for most iterations, resulting in a larger u value t. For sparse features, does not increment much as the gradient value is often zero, leading to a lower u value. Wt plus 1 is equal to Wt minus delta of W eta with under root of u plus exception of t and t. The demonstration term serves to regulate the learning rate eta. For dense features, ut is larger and under root ut becomes larger, thereby lowering eta. This eta is added to the denominator to prevent a divide by zero error from occurring in the case of every sparse features, that is where all the data points yield is zero till the measured instance. Running and visualizing at a grid. Let's plot the two-dimensional visualization of vanilla momentum based NAG gradient descent. Here W and B behaves as two features of the input. X0 and X1 dot B is a dense feature and X0 and X1. B is a dense feature and is always a non-zero value. W is deliberately chosen as a sparse feature with 80% of the values as zero. Thus, we would need a higher learning rate for W and a lower learning rate for B. If not, we will end up with suboptimal paths as shown by the previous types of GD from the figure. Let's look at a visualization of ADA grid. Here, when we compare the both graphs, the above is having lower learning rate and the lower graph which is and the below graph is with higher learning rate. A limitation of ADA grid. First of all, parameters corresponding to sparse features get better updates. You can see in this graph, but disadvantages are the learning rate decay very aggressively as the denominator grows, not good for parameters corresponding to dense features. Running and visualizing RMSprop. Intuition. Why not decay the denominator and prevent its rapid growth? We can consider the RMSprop algorithm. Here, this is the algorithm. Please give a side to this algorithm by pausing this video. We can see from this that our value u is much smaller than in the case of Adagrad. Due to the history of the gradient being multiplied by the decay ratio, the relative difference between dense and sparse feature is still maintained. That is W of t plus 1 is equal to Wt minus eta divided by under root of ut plus e with delta of Wt. Let's visualize RMS probe in two-dimensional. We can see that there is no aggressive decay of P, thus it can reaches the minima. Adagrad got stuck when it was close to convergence. It was no longer able to move in the vertical B. direction because of the decayed learning rate. RMSprop overcomes this problem by being less aggressive on the decay. We have already looked at algorithms that make use of a history term. Momentum-based GD makes use of the history of the gradients. Here, history is used to calculate the current update. RMSprop makes use of the history of the square of the gradients. Here, history is used to adjust the learning rate. Can we combine these two ideas? Yes. In the form of Adam, we uses both of those history terms. In this graph, the black is vanilla GD, and red is momentum based GD, and blue is Nesterov accelerated GD, and green is Adagrad, and brown is RMSprop. As will as with all momentum-based algorithms, there is some oscillations as it approaches the minima value. Adam moves much faster than the other algorithm. You can see in this graph. Variants of gradient descent, running and visualizing Adam. In this slide, we are talking about Adam. This is very similar to the history that momentum-based GD maintains. It's running sum of all the updates done. Here mt is equal to beta 1 multiplied with v of t minus 1 plus 1 minus beta 1 with delta of wt. This is similar to the history that RMSprop maintains. It is used to regulate the learning rate. Wt plus 1 is equal to Wt minus eta divided by under root of Vt plus exception multiplied with m of t. This is what the previous statement we had used. Here the first history m is used to make the update, ensuring that the history of derivatives t is used to calculate the current update. The second derivative v is used to regulate the learning rate based on density or sparsity of t the feature. In addition to the above points, Adam performs bias. In addition to the above points, Adam performs bias correction by using the following equations. It ensures that the training is smoother and also prevents errating updates in beginning of the training. Now, summary. We learn about algorithms which are GD, momentum based GD, Nesterov accelerated GD, AdaGrad, RMSprop, and ADAM. Strategies we go through, and the strategies are batch, mini batch, which is 32, 64, 128, and stochastic. Up till this point, we have been using GD with batch update. In practice, Adam with mini batch is the most popular choice. However, GD with stochastic update is also used along with the use of special strategies to adjust the learning rate. Thank you.